So welcome to the August General Assembly meeting. We are now recording the Zoom call. Our agenda is kind of normal for these meetings. We have a member presentation from Steve Bradshaw. We have a featured speaker from Don Wrigley talking about lunar observing. We are live at the Southeast Regional Library and also on Zoom. This is being recorded, so if you want to go back and watch the presentation again, go to the EVAC website, look under meetings, it's easy to find, and you can watch the Zoom presentation. So, do we have any visitors tonight? Yes, please stand. Let us know who you are. What brought you here? Okay, Troy and Silas, we are glad that you are here tonight and hope you have fun. Anyone else is a visitor? Yes, sir, in the back. Okay, thank you, Daniel. Daniel is with us. I would recommend, we had a couple of presentations in the last couple of months. If you haven't looked at them, go play those Zoom sessions from Sid, and they were lots of fun. So thank you. I'm glad that you are here. Greco is generally open for public viewing Friday and Saturday evening, sunset to 9:30, weather permitting, which is the operating phrase. Adam is trying tonight. He said it was beginning to clear a little. I haven't been outside for a while. Is it likely that it's clearing, or is that just, it's an optimistic hope dream. So do visit us at the observatory or visit us on Facebook because we will announce if the observatory is closed, and that's an easy way to check. But there is information that we post pretty regularly on the Facebook page. Also on our website, we do private viewings. If you know someone who would like to do a private viewing, they're by appointment Sunday through Thursday as available. And then we have returned to the Second Friday Star Party. We tried on August 12th, we got clouded out. So hopefully next month will be better, but we are trying to return to have the Second Friday Star Party. I would recommend also checking out the EVAC website. As we mentioned, the meetings are recorded on Zoom, but we also have a virtual beginners lab, and there's lots of other information on the website that might be helpful. We are doing some outreach Sunday, September 18th. If you're going to the Diamondbacks game, come to visit us at the STEM dugout. The Diamondbacks have had a couple of good games this week, but if the game gets boring, come down and see us. We'll be doing all sorts of STEM activities on the concourse. And other upcoming events, you can see the list here. Contact Alex under events coordinator at evaconline.org. That's her events hat as opposed to treasurer's hat. And we are looking for volunteers. So if you are interested in helping us with school outreach or other types of events, that would be helpful if you can donate a telescope to those and show people things through your telescope. It's a lot of fun. It's a great experience, and it's something the club is well known for. Unfortunately, after COVID, we just have lost a lot of contacts with schools, so hopefully we'll be able to rebuild that pretty soon. Also, Superstition Mountain Astronomical League is doing some viewing also at Lost Dutchman State Park on Saturdays. These are the dates. If you are interested, you could use supermountainastro@gmail.com and contact them if you would like to volunteer. These aren't EVAC events per se, but if you wanted to help out the other club, it's a great thing to do. We do have one bit of business that we need a vote on. This is to change the EVAC membership rates. They are not increasing. What we're doing is turning it into a 6-month option for a discounted structure and getting rid of the weird quarters that we were having to deal with. It just makes it easier for people to not have to worry about change. So the proposal is to change the 6-month window to 15 and 20, and to also add a new student and teacher membership at $20 for new and renewal for students and educators. So we talked about this last month. We had it in the Observer as is required for us to print changes to the bylaws. So is there any discussion on this from the group here, or James will monitor if there are any chat questions? Yes.
I have a question. The proposed family membership from July to December, the dollars more than it was.
It is slightly higher at $250. It's because we couldn't really divide it out evenly. There's no way to divide 35 evenly. And so we figured we would just say, it's still a deal at $20 for a family, but you're correct. Thank you for the math check. There wasn't a way to get $35 to divide evenly, but good point. Any other questions, comments, anything, James? All right, all in favor, say aye. Any opposed? Gordon is in the back doing his secretary thing, taking notes. So that passed, and thank you. This will be added to an addendum on the bylaws. We do have some things going on at Greco. We are looking to build a meteorite display. Brooks is kind of heading this up. He is in the back in the gray shirt. If you have some interest in this, if you have a meteorite lying around that you might like to donate, if you would like to donate to the cause, talk to Brooks. He would be glad to help you with that. We also have a beginner's telescope class. James, do you want to say anything about it?
Yeah, sure.
Okay, so just come up and introduce yourself. You'll be on the camera.
Okay, James here. So we are looking at doing a beginner's telescope class. And it's going to be for people who are just purchased a telescope or ones who are thinking about purchasing a telescope. Is that better? Okay, thanks. And it's probably going to be about 5 different sessions, 5 online, probably Zoom meetings that will be about an hour each, and then 5 labs. We're looking at probably doing on the weekends. That'll be 2 hours each. If that's something you guys would be interested in, please contact myself, James Yoder, and I should be on the website, or Claude. Or
could we do a show of hands, at least in the room? Is anybody interested in? We're just trying to judge. We keep hearing that there's a need for a beginning telescope class. We're just not sure how many people.
Yeah, I guess I can expand a little bit more about what we're going to cover on the classes. Would be different types of telescopes, the parts of the telescopes, things to consider when you're going to purchase one. Also basics of the astronomy, how to tell what constellations are in the sky, how to figure out what you're going to look at that evening. We'll talk a little bit about multiple star systems. What are the appropriate things to look at for your size telescope? A lot of stuff like that, just really basic information. If you haven't had experience with this, it should be very helpful. And we're also looking at a cost structure for it. I think we're talking about $25 for non-members and something like $10 for members. And we're looking at maybe in October, starting to kick that off and finish it off before Thanksgiving. So I guess then we'd ask questions. So does anyone have questions before we do show of hands? Yeah. Yeah, so this will be a pilot one. So we'll be learning a lot, but we are going to record the Zoom meetings. And then after the first one, we'll reevaluate and everything. But that was actually the intent would be at least to have the Zoom meetings available, and those would be free for other students, in the future. But
the other part of that was the lab. And we kind of had a feeling that without having a lab, people would get the information, but they wouldn't have the hands-on experience of trying it out and having a mentor or people around to help them make sure things were working. So while I agree with you about the ability to put it on the website, the hands-on piece we thought was also important. Possibly James would have to decide on that one.
Yeah, so it's going to be 5 different labs, and the lab is critical, right? So it's going to be like 2 hours labs each. And if you have a telescope, we're going to encourage you to bring your telescope. But if you don't, we'll take some of these donation ones and use them. So we will hit probably on one of the Tuesdays, but it will be by itself. And so I think, yeah, the telescope time is going to be critical, because that's where really people get stuck on if you're beginning, is getting frustrated trying to figure out how to use the dang thing, right? So, any other questions? Show of hands of anyone who might be interested, and also chat in this going forward. Okay. I know a lot of you guys already know it already, but if you have friends or something, maybe you can, feed it on when we come to more details. All right, thanks.
And James has done a good job. It's a very thorough class. So I would say even people who would consider themselves moderate level, you're going to learn something, because it's going to be fun and it'll give you some good practice. So it's useful. Our member presentation tonight is from Steve Bradshaw. And I'm going to warn the Zoom folks, we are changing computers. So we will try to do this as effortlessly as possible. And hopefully things will continue to work. But I haven't. Start video. There it is. Here you are. I'm gonna go this way.
That would be a bad thing.
That would be a bad thing.
All right, let me get set up here, folks, and we'll be on our way. So, yeah. Okay. Whoops. I haven't shared yet. I'm working on sharing right now.
There we go.
Share.
Share.
Yep. And
Yep.
are we sharing?
Yeah, but you need to make it larger.
Yeah, I know.
No,
I
you
need.
to go into.
Oh, here, I can just do it right here.
Just- there
All right, we're good to go. All right. All right, everybody. My name is Steve Bradshaw, as you saw. I've actually been a member of the club for just about a year now. I joined this time last year. Got my first telescope about a year ago. So I'm a bit of a newbie. And so anyway, as you can see, I'm going to talk a little bit about Lagrange points in space. I will have to kind of move through this a little bit, because we need to leave room for Dawn's presentation as well. And this one's actually fairly full. So let's just get to it. It's 2 sections. I have sort of an introductory section, and then I'm going to have a section with a bit more detail to it following that. So let's get to it. My own introduction to Lagrange points really is consisting of 2 kind of primary memories. The first one's way back in 1968, actually. I went to see the movie 2001: A Space Odyssey. And at one point in the movie, astronaut David Bowman leaves his spaceship, the Discovery spaceship, parked at Jupiter Io Lagrange point 1. And I was 12 at the time and pretty clueless what that meant. So my second memory is actually much more recent. It was actually at Christmas time when they launched the James Webb Space Telescope. And as you can see, it was launched to the Sun-Earth Lagrange point 2. And I was 66 and still clueless. But all that gave me some ideas that, obviously there's places to park spaceships out here. And so I got curious, did a bit of studying, read a lot, watched a lot of videos, and you get this presentation as a result, is what this is. So the goals of this presentation, the main one, is to help other newbies like me maybe learn a little bit more. There's a lot of new people in the club, and I'm hoping to maybe give them a little bit of knowledge as well. But I realize there's a lot of old pros in the club as well. And so the stretch goal here is to maybe refresh their knowledge. Maybe they haven't looked at Lagrange points in a while. and you're a little rusty on them, or maybe provide a new fact even. Hopefully we'll get lucky here. The presentation is going to illustrate the orbital problem solved by Lagrange points. Lagrange points don't make much sense unless you know what the problem is. They solve a problem, and so we need to talk about the problem a little bit first. Then we're going to talk about how Lagrange points operate, both graphically. I have some graphics and a tad of math, not a whole lot of math, but a tad of math. And then I'm actually going to provide a few examples as well of things that are currently at some Sun-Earth Lagrange points. It's not an all-inclusive list, but some ideas. So anyway, why are Lagrange points important is the first thing here. And as you can see here, they are places to park spacecraft in stable orbits. So what does stable mean though? Stable, as you can see from the second bullet point there, means that little to no energy is going to be required to keep the spacecraft orbiting in these locations. And if you're a spacecraft, there are some benefits to that. As you can see, there is the benefit of less fuel, so that you can stay up a little longer, a little less cost to launch, things like that. And there's also that spacecraft can maintain a continuous view of a specific region of space. And I'm going to try something here. Give me a moment. I'm going to bring up a laser pointer. I'm hoping. It's kind of hard to see. Whoops. I'm trying to click on that little thing and it's hard to see in the corner down there. So I may not be able to get my laser pointer. Oh, there it is. I can see it up here. Laser pointer. There we go. So let me go back here a bit. So anyway, I got a laser pointer now that'll work for the folks on Zoom. And so over here, I've drawn the sun in. You can see the Earth is orbiting the sun. And straight out from that, I've actually drawn the James Webb Space Telescope. And notice that James Webb is oriented so that it's always going to be facing the outer solar system. So if you always want to look out there, you can always be looking out there. You're not ever going to be really facing the sun where it's going to mess up the telescope image and things like that. There are other reasons to use that. That's just one example. Now, Lagrange points are actually going to solve an orbital problem. So let's talk about that for just a moment here. The problem at its core is going to be a result of this law of the conservation of angular momentum. Okay, and I've given you a definition here, but really these are the important parts right here and here at the bottom. So notice that objects that are in lower radius orbits are going to have faster angular velocities. They're going to go through space more quickly. Okay, and if they're in a higher radius orbit, they're going to go through space a little bit more slowly. They're going to have a slower angular velocity. And I've actually drawn examples of this over here with Mercury and Venus and Earth. So Mercury's in the lowest orbit. So it's traveling the fastest through space. It's got the fastest angular velocity. Venus, having a slightly higher orbit, is going to be traveling a little bit slower. And Earth here has the highest orbit, at least in this example, and it's going to be traveling the slowest through space. So these objects are not going to be synchronized. They're going to be traveling around at various speeds around the sun at all times. So there's kind of how that works. And graphically, or excuse me, mathematically, this is the formula for angular momentum here. And I realize that probably like me, you have no idea what L and M and R and P and all that stuff is. So I've actually redrawn the formula down here with English words. So it makes more sense, all right? And here's the way it works. This formula actually provides clues as to what changes are possible in an orbiting system. You just have to be able to interpret the format of the formula. So I'm going to do that for you really quickly. The angular momentum L value is a constant for any given system. So a system would be Jupiter orbiting the sun, the Earth orbiting the sun, the moon orbiting the Earth. That's a given system. And if nothing acts on it from the outside, the angular momentum L is a constant value. It doesn't change the number. It's constant. The idea is it's conserved. It's the conservation of angular momentum. So it's a fixed value. Now, the mass for a given system really isn't going to change much, at least over a short period of time either. Sure, the sun's off-gassing stuff all the time through solar wind and whatever, but it doesn't change over a short period of time. And so that means out of all these variables, only the orbital radius and the angular velocity really are going to be changing as it rules. And here's how it's going to work. We know by definition, this number in this formula can't change for a given system. the mass really won't change over a period of time. So here's what's happening. If the orbital radius goes up, you get a higher orbit, then the angular velocity has to go down or the formula breaks. These numbers on this side are no longer going to equal this number on this side. Okay, and vice versa is true. If the orbital radius would go down, the angular velocity has to go up, or once again, it's not going to equal whatever that number is there, and it's a constant. So this is sort of the math behind that. Now, graphically, it looks like this. What if you wanted to keep a satellite parked next to Earth, but in a higher or lower orbit? Is this going to work according to the conservation of angular momentum? Big no, it just wouldn't work. And so over here, I have the sun again and the Earth. The Earth is orbiting the sun on every 365 days. What if I put a spacecraft over here? What's going to happen? Well, if I put a spacecraft over there, it's going to be in a higher orbit. So it's going to be traveling a little bit slower, and its orbital period is going to be greater than that of Earth. So they're not going to stay synchronized in their orbit. They're going to drift apart over time. That this will drift behind is what will happen. And if I put a spacecraft over here inside the Earth, well, then it has a lower orbit radius. It's going to be traveling a little faster and have a faster orbital period, and it's going to surge ahead of the Earth. So that's what's going to be the result of this law. So what's going to happen here then is this. We're going to have to try to find a way for two different objects with different orbital radii to be able to travel together. And that's known as what they call the three-body problem. Maybe some of you have heard that before. So let's talk about the three-body problem. Sometimes it's called the restricted three-body problem because of the mathematics involved, okay? Now, first of all, the three-body problem can be any three bodies as long as they meet the criteria. So I've drawn an example here of the sun, and Jupiter, of course, is going to be orbiting the sun here, okay, going around. And the first criteria is that the first body has to have at least 25 times more mass than the second body. And there's a very specific reason for that that I'll show on the very last slide. So we are going to come back to that. And the next thing, criteria, is that the third body, so I've added a satellite now, it needs to have pretty much be massless, or at least nearly so compared to the first two bodies. So there's some of the criteria. And by the way, notice that sometimes it's called the 2.5 body problem because it's such a tiny third body. And then in this three-body problem, all the orbits are idealized to circular rather than the more real-world ellipticals. And the nice thing is that Lagrange solutions still are going to work in this environment. So it doesn't matter. We're not forwarding on the slides, and I'm not sure why. There we go. All right, so there we go. So here's how we solve the three-body problem. We do it with Lagrange points. The Lagrange points are the solutions to the three-body problem, okay? And these are locations where a small object can orbit synchronously with another object. Is the idea of these Lagrange points. And FYI, the Lagrange points are not really points. They're actually regions of space where you can have a small orbit, is all it is. And I'm actually going to illustrate that on the next slide. Now, I'm not going to cover all this. This is just who discovered what and when and here. But I do want to point out this illustration over here. So I have the sun, I have Earth orbiting the sun, and I've showed the 5 Lagrange points here. Now, Lagrange points 1 through 3, you can see along this line here. I'm not really going to cover much of 3 because it's no practical value. There's really not much you can do with that point. But I am going to cover the rest of these. And notice I've color-coded 1, 2, and 3 in red because these are known as the metastable points. These are stable, but not quite all the way stable. So that means that if you park a spacecraft at one of these red points here, you're going to need a little bit of fuel, a little bit of thrusters to kind of nudge it back into position every once in a while, or it will drift away. Whereas Lagrange points 4 and 5 out here, they actually are stable points, and no thrusters, no fuel are going to be required to keep objects there. Matter of fact, a lot of the planets, probably Jupiter most famously, have asteroids sitting out here at L4 and L5 in their orbits, okay? And asteroids don't have thrusters, they don't have fuel, but yet the asteroids stay there. Why? They're stable points, they just float along unless something outside kind of perturbs them some way. All right, so there's the Lagrange points. Let's go through. Now, I mentioned on the previous slide that the Lagrange points are not really points. They're small regions where a spacecraft or an asteroid could actually orbit for a bit. So notice I've drawn the Earth in sort of a horizontal orbit here around the sun. So it's kind of going horizontally back and forth here. And at this current position of Earth, these would be the Lagrange points where they would be at that point in time. And notice they are sort of perpendicular orbits to this horizontal orbit. So they're kind of going up and down. Matter of fact, I've got the little James Webb so it can kind of just go up and down there, kind of orbiting of this thing. And they're called halo orbits. And actually, it's a very specific type of halo orbit named this after this guy here, but it's French and I'm not even going to try. So I know I'll butcher that name if I try to go for it. So anyway, so that's the idea of that. Now, as far as usages for Sun-Earth Lagrange point 1, unfortunately, this is in my way. And I'm not sure how to get rid of that. But you can kind of see a little red point right up here. That's Lagrange point 1. Notice it has full access to the sun and full access to the day side of Earth. And so notice what it's useful for. Solar observatories are observing the day side of Earth because it always has access to those things. And there are several examples of satellites that are currently at Lagrange point 1 that are doing, basically in these examples are actually monitoring the sun or the solar wind or something associated with the sun. Now notice that Lagrange point 2, you can kind of see the red dot right out here in my little legend. Unfortunately, that stuff's covering it for you guys here in the room. But notice it always has access to deep space or the outer solar system. So there are lots of things out there currently that are out there communicating or viewing or whatever the outside solar system, right? Deep space. This is actually a communications satellite from China. And China actually has a bunch of equipment on the back side of the moon, the far side of the moon. And so the only way they can communicate is send a signal past the moon, bounce it off this satellite and get it back to the backside of the moon. And they can talk about the moon that way or talk to the moon that way. So anyway, as far as Lagrange points operating, this is the next section, and we'll try to get through here. There are several forces involved in creating these Lagrange points, these parking lots in space. The first two are actually going to be this. They're going to be the centripetal force, and this is the force that it's basically gravity. It's pulling things toward the center. In this case, it's going to be pulling towards the sun. Now, I realize gravity doesn't pull, it bends space and all that, but we're going to say pull just to keep it simple in here. So these two forces, though, the centripetal force and the fictitious centrifugal force, basically are working in different directions, as you can see here. And hopefully you can reach an equilibrium where you can get some stable points as a result. Now, add to these forces a fictitious Coriolis force that I do not have time to talk about in here. That's a whole nother topic. But this Coriolis force is primarily going to be working on Lagrange points 5 and 4. And I will have more to say about this later, but if you are curious about Coriolis force or the Coriolis effect, go search that on YouTube and you'll get the coolest videos. They have some really great videos that show how some of this works. But anyway, this is it. Now, and FYI, this whole thing has to rotate because if it doesn't rotate, you don't get the fictitious centrifugal and Coriolis forces. So this is a rotating system at all times. Now, before I get into the actual Lagrange points, I just want to use this example of the Earth orbiting the sun as an example and kind of a baseline, and we'll launch from that to talk about Lagrange points. So the combined sun and Earth masses here are providing the centripetal force that's pulling the Earth toward the sun, and it keeps the sun basically orbiting, it keeps the Earth orbiting the sun is what it's doing. Now, we could put this as a formula for the mass, showing total mass is shown by the formula, and I'll just do it over here. The total mass that's keeping the sun, or excuse me, the Earth orbiting around the sun is the mass of the sun plus the mass of the Earth and their gravity they generate. And that kind of keeps the sun, or excuse me, the Earth going around the sun. All right, so that's a very important thing. And we know, we're reaching almost the scariest part of the whole presentation. Now we know from past scientists that the total mass of a system is inversely related to its orbital period P. So, okay, what does that mean? Well, it looks like this formula here, and that looks really scary, doesn't it? Square roots, fractions, exponents, It looks like, uh-oh, scary math alert, right? So we got a scary math alert going on here. So I'm going to use this formula a few times. So I want to make sure everybody understands how to interpret this formula. So before I finish the rest of this slide down here, I'm going to break away and talk about that formula for just like 1 minute. So first of all, take a chill. The math isn't that bad. Okay, it really isn't. Because this formula is derived from Kepler's and Newton's work, and it looks scary, but we don't need to solve this equation for our purposes. So we don't have to figure out what P is and solve for P, or we don't have to solve for M or any of these things. What we care about, and the only thing we care about right now, is the relationship between the P and the M variables. And remember, this is the orbital period, and this is the mass. So how is orbital period and mass, or how are they related? And the formula's format itself tells us that P and M have an inverse, not a direct relationship. Great. What does that mean? If you haven't had math in 20 years, or you hate math, or math makes your palms sweaty, you probably don't know that. I know I had to go look it up because I hadn't seen it in a while. If I haven't had algebra in God knows how many years. So anyway, so here's what it is. I'm going to give you a few examples of how to interpolate the formulas. So I gave you 3 just nothing formulas. They're just examples. They don't mean anything. They show you how you figure out a direct relationship. And this is really useful in astronomy, by the way. So this first example here, we have x over 1 equals y over 1. Now, notice the x here is in the numerator of the fraction, and the y over on the other side of the equal sign is also in the numerator. Whenever you see this kind of relationship, it means it's a direct relationship between x and y. And it really means this: if the value of x goes up, the value of y goes up. The value of x goes down, the value of y goes down. And if we change the fraction and put the x and y in the denominator, it still doesn't matter. It's still a direct, straight across the equal sign sort of relationship. It's a direct relationship. And this holds true again. X goes up, y goes up, et cetera. And if we just get rid of the fraction altogether, we see the same thing. They're directly related. If one goes up, the other one goes up. If one goes down, they both go down. Now, that doesn't look like this formula up here at the top at all. Our top formula at the top looks more like this. And this is an inverse relationship in math. And essentially, this x here is now in the denominator on this side, where the y is in the numerator. So going across the equal sign, we have to sort of draw a diagonal line across here. And it means these things are inversely related. If the value of x is going up, the value of y has to go down. Or vice versa, if the value of x goes down, y has to go up. And if we rewrite the fractions this way and just move the x and y's across this way, it's still an inverse relationship. So looking back up here at our formula, this is in the numerator, the P is in the numerator, the M is in a denominator. It's an indirect relationship. So if mass goes up, orbital period must go down. Or if mass goes down, orbital period must go up. So that's how you would sort of interpret that formula. Now, what that's going to look like is this, and I kind of put it finally back on this slide. And remember, this is mass, this is orbital period. So the main point, mass is one of the main determinants of orbital period. So unless you change the mass or have some sort of outside influence, perhaps, you're not really going to change the orbital period of Earth or any other object that's orbiting. All right. Now let's add to this a Lagrange point. So here's the sun, here's Lagrange point 1 in between the sun and the Earth. The Earth has an orbital period of roughly 365 days. And so compared to Earth, a satellite that's orbiting out here has a reduced orbital radius. It's got a smaller orbital radius than from the sun to the Earth. This is shorter. So we know that this object orbiting here probably is going to have a higher angular velocity in a shorter period. It's moving faster. All right. And so the fact is, though, at L1, and specifically here in this L1 region, an object does not have a shorter period. What? Why? How did that work? That's because the mass changed, which is why I went all through that mass stuff. Notice the mass felt here at L1 is the mass of the sun, because the sun's pulling on this object, minus the mass of the Earth, because the Earth is pulling in the opposite direction. It's a tug of war. And so since the mass has gone down, M has gone down, the orbital period goes up and ends up at L1, and specifically at L1, the orbital period matches Earth. So they can travel together through space. Okay, now if you prefer pictures, not this picture, but a different picture, you've probably seen something like this before. I know I have in my studies. They just draw a flat grid. Doesn't look flat because the line's got a slope here, but this is supposed to be a flat grid. Here's the sun. They grid a gravity well here. Here's the earth. They put a gravity well beneath that. And this two-dimensional analogy is supposed to kind of give you an idea how four-dimensional space-time's working, is what this is. But it breaks down a little bit because it's only two dimensions. But notice the sun's mass creates a gravity well that curves space and pulls objects toward the sun. If I put a marble here, I will sit. If I put a marble here, it'll just sit. But if I put a marble here, it's going to roll into the hole. If I put a marble here, it'll roll into the hole. Or I put a marble here, it's going to roll into the hole, just like it would for sun, or the Earth's going to pull it in as well. But notice that an object at L1 is balanced on this little saddle point right between the gravity wells. And as long as you can stay perched there, you can keep a fairly stable orbit without a lot of fuel. Occasionally, you'll need a little bit of fuel to nudge it back up onto the hill, but it's pretty stable. This is one of those meta-stable points. It's not entirely stable. Now, remember also that this entire system is rotating, which means the L1 saddle point is going to rotate as well. So I've just lost something here. I'm not sure what that is. There we go. So it's just going to rotate, just so you can see the saddle point between the gravity wells is just kind of traveling around. So that's a little bit about L1, much as I can say in the time allotted anyway. Now, what about L2? L2, notice, is outside the Earth, parked out here. This is where James Webb went. And compared to Earth, the satellite at L2 has an increased orbital radius. It's further out from the sun. It's further out, which means it should have a slower angular velocity and a longer orbital period, and shouldn't travel, anything out here shouldn't travel with the Earth. It just shouldn't. But turns out at L2, and specifically at just L2, an object doesn't have a longer orbital radius. Why is that? Back to that mass stuff again. Notice the mass at L2 now is the mass of the sun, because the sun here is pulling on L2, plus the mass of the Earth, because the Earth is pulling on L2 simultaneously. So as far as we're concerned, the M here has gone up, so the P has to go down. The orbital period has to go down, and that means that the orbital period at L2 and only L2 matches the orbital period of the Earth. So they travel together. That's why James Webb works so well. It just sits out there and travels with the Earth. All right. If you like the more rounded pictures or whatever else, for L2, you must also consider, and for everything actually, but for L2, it's a good time to introduce the centrifugal force caused by the rotating system. It's shown in the graphic by a curved surface. So notice we have this upside down bowl here. And if I put a marble here, it's just going to roll off. And if I put a marble over here, it's going to roll off. Well, the Earth and anything at L2 wants to roll off too and get away from the sun because of the centrifugal force. All right. But once again, if we balance the centrifugal force against the centripetal force created by gravity, then that becomes a somewhat stable point. Notice it is metastable. It's not a very big area. Occasionally you got to nudge it back into place with a little bit of fuel, but for the most part, it's pretty stable. And again, this entire system is rotating. So that means it's going to look like this in the real world. And notice that saddle point just sort of travels around with the objects as they move around, right? Last two slides, actually, and then we'll get to Dawn's. I'm skipping Lagrange point 3 out here in the orbit because there's just no practical use for it at this point in time. But L4 is up here. It precedes the Earth in its orbit. L5 is out here. It follows the Earth in its orbit. And notice that compared to Earth, the satellite at L4, L5 has less mass. So it should have a larger orbital radius and a longer orbital period. That's what it should have. But specifically at L4, L5 again, an object does not have a longer orbital period. Why the heck is that? Well, because an object at L4, L5 feels force vectors from both the sun and the Earth, but in different directions. So notice what I've drawn here. This is the force vector from the sun, kind of, we'll say, pulling on this object at L4. And I've drawn a really long arrow because it's a really big force vector. It's a lot of gravity from the sun. But the Earth is actually pulling a little bit over here on this point as well. But it's not pulling as much, so it's a little arrow, itty bitty arrow, right? Now, it is perfectly acceptable mathematically, as I've now learned, that you could redraw the force arrows like that. And it points to someplace inside the sun here called a barycenter. Brand new word for me. What the heck is a barycenter? The barycenter is the $5 word that talks about the common center of mass between two objects. So the Earth is actually not orbiting the center of the sun. It's actually orbiting this barycenter. And actually the sun is orbiting the barycenter as well, but it just results in a little bit of a wobble is all it does. And the barycenter is a dynamic point. Because the Earth is over here right now, the barycenter is on this side of the sun. But if we were to have the Earth up here in its orbit, the barycenter would be at the top of the sun. If we move the Earth over here, the barycenter will be over here or bottom and around. So the barycenter tends to move around as the Earth's moving around. So it's a dynamic point. Now, the thing that's nice about this is that the orbiting the barycenter means that objects at L4 and L5 have a smaller, slightly smaller orbital radius, which gives them a shorter orbital period, which means that their speed matches the Earth and they stay in basically that position relative to Earth the whole time. So that's what's going on there. And if you like this picture instead, we'll do this. And this is my last slide. I lost my laser. There's my laser pointer. So for L4 and L5, you must consider the balance between the centripetal and centrifugal forces. So here's L4 and L5. You notice these are bigger areas right away than these little saddle points are here, here, and here. Okay. But anyway, it's shown in the graphic by the curved gravity well. So we see that. And I do want to point this out. These little circles here, this is L2, this is L1, and this is L3. And notice these are on saddle points, and they're very small. That's why one of the reasons why these are metastable points. You got to nudge a spacecraft back into position every once in a while. They're really small. But these L4 and L5 hilltops are huge by comparison, which makes these stable points. Things can orbit there, like asteroids. They don't have fuel, they don't have thrusters, they stay there, okay? But it's not just the larger area that makes these things more stable. There's also a Coriolis force that works predominantly on L4 and L5 that causes objects to circle at these areas as well, that Coriolis force. And it's actually the Coriolis force at L4 and L5 is the reason why this object here, the main body object, has to have 25 times more mass than the second object up here. Because if this doesn't have at least 25 times more mass than this object up here, these hilltops get really small, very tiny. You lose the Coriolis effect and they're no longer stable points. Now, I'm going to play a little video here in just a second. It's just mostly going to spin this thing. You've seen that a couple of times now. But right at the end of the video, it happens really fast, so don't lose it. The last 2, maybe 3 seconds of this video, they're actually going to increase the size of Earth here so that it's no longer at least 25 times less massive than this object. So as they increase the size of Earth in the last couple seconds of the video, watch these hilltop areas. And it's hard to watch them because they're going to be spinning, but they'll actually shrink up as Earth grows in size. And so you lose the stableness, you lose the Coriolis force. So here I'm going to start the video. It's going to spin. And like I said, in about a couple seconds, you'll see the Earth begin to grow and those hilltops begin to shrink. And there it is right there. And they're shrinking up. So that's the reason for that one thing about being 25 times more massive. And with that, if you have questions, I haven't seen the Zoom. I'll try to answer any questions in the Zoom that I'm able to answer. And if you have questions out there, in interest of Dawn, I'm going to just step aside and I'll answer your questions after the meeting if I can. Anyway, that is it. Thank you.
So we're going to need to. I'm going to need to swap. So see if there's any questions there or changes.
Okay.
See if there are any questions. Come to the, Steve, come to the mic because they won't hear you on the Zoom.
Okay. Okay, what was that again? It's not actually that small. We're talking a pretty large area of space, like, but no, there's no worries about it getting too crowded. So, anything else? Yes.
What about Mercury and Venus? Do they have any impact on them?
Everything impacts a little bit of everything, but no, Lagrange points 4 and 5 will be stable around Earth regardless of Mercury and Venus. So, anything else? All right, thank you very much. I'll sit down and Dawn, wherever Dawn is.
Not yet. Not yet.
Not yet? Well, you're on your own.
Got it. Almost. So are we back? So at this point, just wanted to wish some birthday greetings. Voyager turns 45 this year. Voyager launched on August 20th and September 5th in 1977. How many of you remember who was president in 1977? Jimmy Carter. Okay, so some of you, how many of you are less than 45? Okay, there are a few. Okay, so yes, so we are certainly want to wish Voyager happy birthday. This is an older slide. They're both actually past the heliosphere now, out in the deep space, and Voyager 1 had some issues with its antenna recently, but we are sure that Voyager will have a long and prosperous future, and the Star Trek fans will get that joke. Our September speaker is Kevin Schindler from Lowell Observatory. And then our speaker tonight is Don Wrigley for Lunar Observing. And we're going to stop just for a minute to see if I can get that annoying one off of here. And so James, you want to stop just for a minute? Record again. Okay, back again after our technical changes. Our presenter tonight is Don Wrigley. He's a former president, and I think every other officer for EVAC.
Except the treasurer, which they just don't seem to trust me with.
That could be an option. We might keep that in mind. Don also is very active at the observatory and with our school outreach. So Don Wrigley, you're set. And this just should just forward it.
Clicker?
Yeah, and you're in business.
All right, well,
I'm gonna do one thing
yes,
before you get started. I'm
Yeah.
gonna change this video
oh, okay.
so that people can see you through there.
Oh, okay, and I
then-
still can use that as my pointer? Okay, well, last time I was here speaking, it was 11 years ago, 2011. Before that, it was year 2000. It was 22 years ago. So I seem to be on an 11-year cycle here. I don't know. I expect if you miss this and come back in 2033, and I'll be back. Okay, so originally it was advertised as Lunar Explorations, which I thought was a bit pretentious. And so I changed it to what it really is the things I like to look at and why. And reasons change over the years. First of all, you'll never see the moon like this. This is a lie right here. When I was 10 years old, I got my first telescope. I honestly believed that's what I was going to see. But this is just a compilation of different photographs, okay? Because you'll never see the moon full and with all of these craters showing like this, okay? In case you've never checked it. So that's just a good starting point. And this is a great picture, and just about everything I'll be talking about tonight, you can see it, the scale, okay, with a small telescope. Well, some of the things are really small, you need a bigger telescope, but most stuff is fairly large. Let's talk with a few little factoids about the moon. Let's see if I can, if I do it here, which way do I point?
One second.
Oh.
I'll try this.
Oh,
No.
I can just click that.
No, it should. That should work.
Okay.
And now that should work.
And that should work. Okay. Couple of facts about the moon. Because the moon makes one complete rotation on its axis, whoops, let's back this up. On the same amount of time it goes through all its phases, it always shows the same face. This is synchronized, and it's a lot of moons are that way. But we only get to see this one side of the moon all the time. And so as a result, there's no dark side of the moon except the side that's facing away from the sun, but there is a back side, which we did not know about until, well, the Russians sent their first lunar observer to the that took pictures of the far side. And then later on, we had lunar orbiter photographs. So this was completely unknown to us prior to 1959. There were all kinds of speculations about civilizations on the far side that kept hidden from us, all of that stuff. Well, they aren't there. Okay, thank you. All right, so let's click here. The moon's orbit is elliptical. At its closest point, it's about 224,000 miles. Whoa, I gotta stop doing that. At its furthest point, it's about 251,000. And these two images here pretty much show you the difference between in actual size between the regular moon and what we call the super moon now. Okay, and this is important. Also, because it's an elliptical orbit and because it rotates at the same speed that it goes around the Earth, the part that faces, if you took the central meridian of the moon, okay, it actually points toward this point that's near the center of the ellipse rather than at the Earth.
If you're wanting to show it on that, it's going to need to go there and you'll need to look at it
What's
Yeah.
that?
for them to
Oh,
see.
oh,
it,
okay,
because
I
this
see.
is on
Oh,
your
I got to look
screen,
up there to do this. Okay, thank you. I didn't know, I wasn't looking up there. I was just looking at the screen. So this is the part that's pointing toward the center of the ellipse rather than toward the Earth. So we get to see a little bit on this side of the moon, the east side at one point, and what happened to my pointer? And you get to see a little bit of this side. These are called librations and longitude, okay? Because it's really the face of it, the center is facing toward the middle. We get to see a little bit on each side. And these librations and longitude come in very handy for lunar observing. Second thing we face is the fact that the moon's orbit is tilted slightly with respect to the Earth's orbit around the sun. It's about 5 degrees. Let me see if I can get this thing down here. Okay, you can see the Earth is tilted at a 23.5-degree angle in its orbit around the sun. Now, most moons in our solar system follow the equator of the planet they're on. Okay, Jupiter's moons are on its equatorial plane, Saturn's moons. Okay, but because our moon is so much more massive relative to the other moons compared with their planets, if that makes sense. Okay, it's about 1/6 the mass of the Earth. It makes its own. It doesn't have to follow our equatorial plane. It follows more or less the ecliptic, but it's about 5 degrees off, which means that sometimes we get to look up underneath the moon when it's above, okay? And sometimes we get to look down on top of the moon. These are we call librations in latitude. So in effect, the moon, they say the moon nods its head up and down, okay? And in latitude, it turns sideways in longitude. So in all, we get to see about 59% of the moon's surface. So you can see here, well, I got to use your point here. This is a good northern libration. You can see see the distance between Tycho and the hand compared with this libration, where it's nearly much closer. So these librations make a big difference in what you'll see when you explore the moon. Okay, let's flip over here. Also, it goes through phases. This is called the Oreo cookie model of phases. It's for the second grade science class. This is how the teacher presents it to the kids. This is what it actually ends up being. Not quite as neat. Their little mouths can't quite make those shapes right. I like this one because he threw in a comet right there, through a little comet, you see, and a little planet Earth. But anyways, even this is to get the kids to understand, and they get to eat it afterwards. I was in a second grade class when we were doing this project, and they loved it. So anyways, the phases are important because it means that the moon is changing. Every night you go out to look at the moon, you're going to see something different. And because of libration, every month you go out through the same phases, and they never look quite the same. You're always looking for something different. You can look at an object 100 times and it'll look different every time. It's never going to look exactly the same. I'm clicking through stuff here and I apologize. Okay. This is about mostly when I do most of my observing is between about 4 days and maybe a couple of days after full. So this is about a 12-day cycle when I do most of it. I don't observe third quarter because I had to get up at 3 a.m. Okay, which to me is either too late or too early. Okay, it falls somewhere in between. Anyways, at 3 a.m., I'm usually in bed. And so I'm not out looking at third quarter, or I don't get up that early. Now, the phases we see, and a lot of people don't understand this, the phases we see are not caused by the Earth's shadow. This is clicking on its own. Here's a good example. Here is our very early phase, okay, this is the new moon in the old moon's arms. You've heard this expression. This is lit up by Earth light, okay? Light reflects off the Earth and lights up the side of the face of the moon, because when the moon is new, they're seeing, if you were living on the moon, you'd see a full Earth, okay? It'd be fully illuminated, and so it's much brighter, and it lights up the place pretty good. This is a photograph taken at the beginning of a lunar eclipse. You can see that it's nothing shaped like it. Okay, the phases are due to the angle of the sun and nothing more. But a lot of people still get confused. This is a photograph somebody did. They had somebody stand up and hold a ring, which is the size of the Earth's umbra, and they had just put it in front of them just to see how big the Earth's shadow is. Okay, that's why when there's a lunar eclipse on your side of the globe, everybody gets to see it. Okay, it's not like a solar eclipse; it's just a small group. Okay, so why look at the moon? Maybe you can spend some time with Dad. I love this picture. That's a Newtonian that they're looking to that's facing the wrong way. It's easy to locate. That's one reason I got started with the moon is that I could find it. Okay. It was, sometimes with the observatory, I don't know if this is on a timer and it's going itself. Is that it? Okay. Anyways, the observatory, sometimes that's the only thing we can see through the clouds, but we still get to do some pretty good observing, even when it's cloudy. Okay. It's out a lot. And for people, the deep sky observers will tell you that's the case. And I'm probably about half the month I'm able to observe the moon. Okay, the rest of the time it's too thin a crescent or it's up too late. And you don't have to worry about light pollution. It's not an issue. And yeah, you can use, you don't need to have really big expensive equipment. I don't know who these guys are, but I hate them. Okay. A little 70mm refractor will do the trick for everything on the, and I'm going to try to relate some of this to our Lunar 100 list, our club's Lunar 100 list, because everything on our list, except maybe the little craterlets near Copernicus, you can see with the 70mm scope. This one here shows you the typical low power view of the moon and the size of the planets when seen at that powered. You can see it doesn't take a powerful telescope to get useful views of the moon, whereas to look at the planets, they're pretty tiny in comparison. So I remember back a few years ago when they said Mars would look as big as the full moon. Do you remember that? And of course, what they meant was if you look at Mars with a really powerful telescope, you could see the same amount of detail as you could see on the moon with the naked eye. But everybody was out looking for Mars to see if it was going to be as big as the full moon. It never is. Okay, so there's a lot to see. And this is, I will show you more about this picture later on. Let's see. I call this part of the talk, Martin Mulls a Moon. And I just did this one for the kids a few years ago with apologies to a certain children's book author and a comedian. Let's look at what we can see. Okay, here's our full moon. And whoops, back it off. All right, let's see. These are all the Maria, okay? There's Mari Crisium, Fields of Fertility, Mari Fecunditatis, Sea of Nectar, Mari Nectaris, Sea of Tranquility, where the Apollo 11 landed, Sea of Serenity. These were named by Riccioli in the late 1600s, okay? And those names have stuck. Several other people, after the discovery of telescope, drew moon maps and named these things because they were not named before that. But these names have stuck. I make up, whoops, I hit the wrong thing. I made up a little saying for these, okay? And it's just to help me remember, and you can laugh, but don't be cruel. But let me get that pointer back over here. I say that chicken feed never tastes sweet. Okay, the stupider these things are, the more likely you are to remember them. That's what I've learned. And so that goes clockwise from Chrysium to fertility, to nectar, to tranquility, serenity. Over here in the western section, you have the Nubium, you have the Homorum. The Oceanus Procellarum is a large area, and the Mare Imbrium. And I made up another stupid saying for that. I say that Newtonians have optical problems inherently. I'm not even sure if that's grammatical, but it's stupid enough to count as a memory device. Okay, so I'm going to start out right up here in the northeast with the Mare Imbrium, and let's do a close up on it. Okay, here we are. It's naked. It's visible to the naked eye. It's one of the biggest objects that you can see with the naked eye. Down here is the Sea of Fertility, the crater Lagrange. This is the Palus Somni. Is a neat little thing. It's really not. It's really more of an optical illusion. The crater Proclus is right here. It's a bright crater that hit at an angle, or the object hit at an angle, and kind of made this side look like this is a separate object, but it's not. I'll back this up. Okay, up here we have craters I always visit when I'm looking at this phase of the moon. Cleomedes, Burckhardt is a neat crater, and Masala. Burckhardt is one of those craters that's I love to use this when the kids are at the observatory, because you have a crater. Let's see, whoops, I'm trying to get this back. We have a crater that landed between two craters that are of the same size, and it just happened to position itself so it looks like it has two big ears. Kids love this. So this is kind of a fun thing to look at. And a lot of the stuff I look at is just fun stuff. Here's my own photograph. I've got several of my own photographs. You can tell because they're not good. Okay, whenever one comes up that's fuzzy and not very good, it's mine. But I show it because it's a really good Eastern libration. Okay, normally you see a Chrysium, you don't see much beyond it. But this is the Mare Marginis, the Mare Smythe, and the Mare Undarum. The Mare Smythe is, you seldom ever see that. I happen to grab in its full. You might see just the edge of it, but I got the whole thing here. Over here is the Sea of Fertility, the crater Lagrange. Lagrange is famous. Well, let me back up here a little bit. This was one that was taken by one of the spaceships. It shows the Chrysium, and it shows Marginis and Smythe in their entirety. But if you look at Chrysium, you'll notice that it looks circular here, okay, but it should look elliptical, but because of foreshortening. But in fact, it is elliptical going the other way. And when you foreshorten it, it looks like a circle. Okay, it's one of the things they found out, and they didn't even realize this until they started orbiting the moon and taking pictures of Chrysium directly overhead. And it just never occurred to them that it was an optical illusion, that it appeared round when it was actually should have been foreshortened. Okay, let's look at the big three. We have Lagrange, Vendelinus, and Petavius. All of them are kind of interesting. I'm going to concentrate on first Lagrange, which was famous when the Apollo 8, I don't know if you remember when Apollo 8 did that little Christmas Eve broadcast, and they flew by Lagrange and showed that. Also, Van Langren, for whom the crater is named, was one of the first people to make a lunar map. And so he was the one who came up with the idea of naming the craters after famous scientists and people. And so he put the biggest one, named it after himself. And then later on, why not? Later on, when other people made maps, they changed all the names, but he managed to keep this one in there. So he's got one of the most prominent craters on the moon just because he drew a map. Petavius is neat because it's got that nice, somewhat larger and older than, whoops, I'm having trouble with the equipment here. Somewhat larger and older than Lagrange, but it has that nice little central crack in the floor that runs right from the central mountain ranges to the edge. Okay, now in the Sea of Fertility, which is just now to the west of these guys, are the Messier twins. And this is a simultaneous impact, okay? Well, two craters, two objects hit the moon. This crater is like 6 miles long, and you can see that it splashed out stuff to the sides, but it did not leave a major hole. It's an elongated crater. This one here sent out 2 rays forward, and then it has this little lip on it. Earlier observers thought that maybe there was a crater here, and then these two came and this one overlapped it. But it turned out the studies done by NASA showed that you can get this same effect. They had high-speed particles, and they shot them at different angles, and were able to create this lip effect that we see, and also this multiple hit thing that we often see on the moon. So my next one is the crater Goclenius. I'm on back up here. This is what the site of the other lunar X. I don't know if you've heard of the lunar X that people see when the moon is about, it's about first quarter, and it's the lunar X is kind of overrated, but it's just where 4 crater corners meet and they shine up real bright. Well, this one here is a little harder to see. Back in, again, with the first lunar orbiter, the Apollo 8 rather, they sent back this picture showing Goclenius with these graben crossing it, okay? Some of them are parallel, and over here they crisscross, and then they showed us this is Magelhans and Magelhans A and Colombo. This is my photograph showing the same region. Part of the nomenclature that came under Riccioli was that large craters, you could have, there's Goclenius, there's Magelhans. If you have a smaller crater nearest, you can just give them A, B, C designations. And on the chart, you'll see the A is, they usually have the letter on the outside of the crater pointing toward the one for which it's named, okay? Sometimes it's a little hard to figure it out. So down here we have the edge of the Mare Nectaris. Okay, now we're moving further west. So let's talk about Nectaris. There's the whole thing. There's the crater Theophilus. This is a crater that was like on the edge of it, but it's half of it's gone here. We'll talk about that a little more. It's called Fracastorius. There's a little scarp right here, and I'm going to show you another picture. It's another one of mine. This one's called Piccolo Mini. It's actually the deepest crater on the moon. It's about 18,000 feet from the bottom to the top of the rim. So it must have had quite an impact. And you can see this little line here that's called the Atlas Scarp. Let me show you. Here it is. There's the Mare Nectaris. There's the Atlas Scarp. There's Piccolo Mini. And, I'm trying to back up here. We're going to look at the whole thing. It was Eugene, what's his last name? Yeah, Shoemaker, who noticed in the 1950s, he started paying attention to these things. He was very interested in the moon, and he made note of the fact that most of the Maria are very round. Okay, and when he come to the Mare Nectaris here, and he saw this scarp, he realized it was concentric with this roundness of the Maria, and he came to the conclusion that it was all related, okay, that this was an outer ring to what was a giant impact basin, and he couldn't get a lot of attention there. There was another example of such a thing, which was called the Mare Orientale, which is on the very far western edge. And it consists, this is a very good photograph here, showing the several layers and the central crater, but people didn't believe him until the first lunar orbiter showed this bullseye ring effect that is in fact, here's another shot of it, taken more recently, the central portion, a mountain range, a flat area, another mountain range, another flat area, another mountain range. It has something to do with what happens when large objects hit the moon very quickly. At first, and I'm no expert at this, so I'm not going to go into all the little details of what happens. I got this one off the internet, and I'm just going to go through it quickly. At first, it's the same thing. You get a compression wave for larger objects, okay? You will get, or rather for smaller objects, it splatters out, you get a little melt, and you end up with a bowl, and it's simple as that. But for larger objects, you get a rebound in the middle that comes up as a central peak. Sometimes you get a central ring instead of a central peak. So basically, small craters are kind of shaped like bowls, or more like cone shapes on the inside. The ratio between the depth and the diameter is much greater when it's smaller than when they get, the larger they get, the smaller that ratio gets, okay? They might be deeper, but the ratio of the diameter, for instance, Copernicus diameter is like 60 miles. And so its depth is only, 8,000, 10,000 feet. So they have more like the shape of a if you pressed a dime or a quarter into clay, you'd have a very small depression compared to larger ones. This is, that's the crater Tycho, and it has not just one, several central peaks. So when you have a really large object, what you get, you will not only get, these cracks go way down deep inside for the basin. So you've got a center, you got one little mountain ring, you got another flat area, you got another mountain peak, then you got another flat, and then you get another one, and they can have 3 or 4 rings. And back before the moon warmed up, okay, this is now we're going back about 3.8 billion years. The moon kind of looked like this. And what happened was the interior of the moon was heating up due to the breakdown of, atomic radioactive materials. And eventually it got hot enough so the interior became molten lava, and it squeezed up through all them big crevices that were caused by these giant impacts. So you can go back here and look at all the major, there's Mare Crisium. And even today, you can see some of this outside ring. Mare Imbrium, they've been able to track the outer rings. This is the Sinus Iridum, which will appear, it's partly buried. We'll see that later on. Even some of these features back here, you can see. Here's the Mare Nectaris. There's Fracastorius sitting on them. What happens when objects hit along the edges of these impact basins, because they were curved, the craters were curved, they were tilted. And so when the lava flowed up and filled the basin, it filled half the craters. That's why you see a lot of semicircle craters on the edges of these impact basins. Let's see, down here is the Zuchius Schiller, one of which is still visible today. I don't have a picture of it, but you can still, if you do some lunar observing, you'll be able to see some of these things. And I look for these things. Now I look for these evidence of outer rings. Okay, all right, I'm going to move a little further east. One of my favorite areas is this little area at the western part of the Sea of Tranquility. We have Ritter and Sabine right here. And I forget which is which. It sort of sounds like a law firm to me, but I can't remember which one. But this is a case of what they believe is simultaneous impact. Okay, I love the symmetry here because you have these two craters that have come back here, the exact same morphology. Okay, inside, there's no splash over between them. It's almost a ridge between them, which indicates the same size objects hitting at the same speed at the same time. I think this is Ritter A and B. Arago up here is a good sized, medium-sized crater, and it has these two little domes that you can find, kind of volcanic domes. Over here is the crater Ariadaeus and the Ariadaeus Rill. We're going to follow that later, but down here you can follow the craters, which are the only 3 craters named after living people. The Apollo 11 site is right here, And these three little craters were named after Aldrin's, Cauldron, and Armstrong. And on a night of good seeing with my 8-inch, I can just make them out. I've seen them a few times, but I can't always count it because the seeing's not always there. So one of the things I look for. Here's another view of Tranquility. And up here is the bottom part of Serenity. Bring this back. The Ariadeus Rill, we're going to follow that right through till we get to, and I'm tilting my head here to see. This is Julius Caesar and Sosigenes, and there's Ritter and Sabine. So Ariadeus is in here. I can't see it from the way I'm tilted here, but if we follow that little rill, okay, it goes right into the sinus medii. And this is actually what we call a graben, okay, where there's been a shrinking of the crust, and it separates and the middle drops out. And so it follows the terrain. You notice it follows over hill and vale, and it just finally peters to an end here in the sinus medii. This is the crater Hyginus, and this is the Hyginus Rill, which is completely different. This is a series of little craters of volcanic origin. Okay, this area up here you can see is darker, and that's volcanic area. Whoops, see, it's 3 jumped ahead. Down here is the crater Triesnecker. This is one of my favorite areas. We have this series of rills here, and these are collapsed lava tubes. It looks like they're emanating from Triesnecker, but actually they have nothing to do with it. But on a good night, we can follow. They're very small. They're very tiny, hair-like things. But on a good night, you can follow these all through this whole area. And it's just kind of a fun area, something to look for on this part of the moon. Okay, let's look at the Sea of Serenity. And it's well named because there's very little going on here. Very little to see. The only thing I can think of is that this was laid out by surveyors. Look at the way they line these right up. And these 4 craters, the only craters you can see, and they're all pretty well lined up. Down here is a crater called Linnaeus. Here's Linnaeus. Back in the 1800s, when they were first getting powerful telescopes, they weren't looking at the big picture. They were always looking for the tiniest thing they could see. And Linnaeus was a crater that was well known and mapped, but in the 1860s, some astronomer announced that it had disappeared and instead was a white spot. And everybody bought that. It's a crater that you don't always see. There's the white spot, but you can see it. Sometimes I look at that area and I can't see Linnaeus. All I can see is the white spot. And so if I didn't spend a lot of time looking, I'd say, gee, you're right, it's disappeared. But it never disappeared. And I found this in guidebooks written in the 60s that it was a mystery they hadn't solved. So this guy didn't spend a lot of time looking at the moon. If you take your time, you'll see it's just a fairly fresh crater, and it has a white ring around it, but there's definitely a crater there. The Apollo astronauts made a point of flying over Linnaeus and taking a picture so everyone say, see, it's still there. It's a real crater. It's not a figment of imagination. Up here is the Valentine Dome with a little T structure of little hills there, which I have trouble finding. It's something I'm always still looking for things. Let's look at the Mare Imbrium. This is one of the larger impact basins. This is an overhead view. There's the Sinus Iridum. Okay, remember that big crater I showed you? Well, here you can see we can only see half of it here. Okay, these craters existed before the lava filled up. So you got Plato and Archimedes that are filled nearly to the top. Plato, right here, is fun to look at because it's got 5 or 6 little tiny craterlets inside, little bowl-shaped craters that are a challenge for any size telescope. You need really good seeing, and I always look for them. You've got 2 individual mountain peaks. The individual mountain peaks are very rare, Pico and Python over here. Back in the 1800s, Naismith, one of these a lunar astronomer, used to make plaster of Paris models of these things. He'd studied them and made these little models. They were much sharper than they are, in fact, when you get a picture. There's the straight range. I remember Pico was the one that's near Plato. They both end at O. Up here, we have the Alpine Valley. Let's look at the Alpine Valley right here. And I've looked at that at high power. It has a little rill going right down the middle. I've only seen it once. I always imagine myself taking one of those little lunar rovers and driving down through the Alpine Valley, take a little trip through there. These two craters at the end of the Alpine Valley are interesting. They have a little line between them. And that's another case of a simultaneous impact. The reason they think that is they've done studies at NASA without simultaneous impact. Whoops. And here's a couple of projectiles, and they develop this little ridge between them. So, and if they see two craters on the moon with that little ridge between them that close together, they assume it was simultaneous, because if one hit and then another one hit, excuse me, it would just partially obliterate the other one's wall. But if they're simultaneous, they create that little ridge that comes up between them. Okay, this is the Apennine Mountain Range, which is on the southeastern portion of Mare Imbrium. By the way, if you look at older maps of the moon, north and south are the same, but east and west was depending on where like west was on the left, was on the right side, because that's where the western horizon was, and east was on the left side. But back in 1960, because they were planning to go to the moon, they decided to change it so it would match like a map. So they switched east and west, which is why the Mare Orientale, which is the eastern sea, is now in the west. They didn't move the Mare, they just changed their directions, the way they measured it. Okay, let's look at this. We've got a neat little mountain range. This is Archimedes. This is Conan, and this is Malicious. And this is this little, if you follow this little thing down here and you come to this little plateau, you come to one of the most difficult ones on it's the Sky and Telescope list. It's called the Ina Caldera. And here's that little plateau here. I've seen this once at 600X, little D-shaped formation, and it's some kind of caldera. We don't know what it is, to be honest with you. It looks like, a close-up looks like you took plaster of Paris and just kind of scraped over it with a paddle. It's kind of looks like stucco. Okay, so to find, at lower, smaller instruments, 400 power, 300 power, you can see a little hint of the D shape. Okay, so there's what it would look like. Here we have the Hadley Rill. This is where the Apollo 15 astronauts landed. Here we go. Nice view of the Hadley Rill. Let me forget my pointer. They landed here. Okay, well, come on. This is the crater Hadley, Mount Hadley. I think this is Hadley Pass, Hadley Gorge, Hadley Plains. I'm just making those up. But I suspect that someday there'll be, if you go right to the base of the mountain, if they ever do colonize the moon, I'm sure there's going to be a Hadley Bar and Grill right about there, because everything else is named Hadley. They landed right here. Let's get this up. And they drove their little buggy to several points along, and then they drove it all the way to the back, and they took this picture of that little elbow, the curve. There is part of the Mount Hadley, and there is Mount Hadley itself. The light was coming from the back, so it appears in shadow. That's one of my favorite shots. I always wanted to go there and take a ride down through that little gully. Okay. While I'm at it, listen, the north and south poles are libration zones. So let's take a look. How do you get there? Well, if you remember, this is Plato in the Alpine Valley. Up here, we have one of the few square craters on the moon. Okay, you see it's called W Bond. Let's do a close-up here for a good libration. I always thought the W stood for Ward Bond, but it's I think it's William Bond. Okay, this one is Maton, and this is kind of a hard one to explain because it looks like a four-leaf clover. Supposedly, you can't get four craters that will do this, where the adjacent walls all melt together, but it does. Scoresby, and then you just follow Chalice, Maine. This one is Bird, and the very top one is Perry. Okay, and named after the two explorers. And the North Pole is, I keep losing that, right about there. This is a nice little dramatic photograph showing the same thing at not such a good libration, but the overhead view from the satellite shows the pole right there. So with a good libration, it'll come down low enough so you can see that. Okay, let's go to the southern part of the moon, two important craters, Tycho right here, and I was glad to see Tycho as his main crater. It's one of the fresh craters on the moon. The ray system extends halfway around the moon, a massive ray system. It's got a great central peak. It's very bright. Clavius is it's an older crater and one of the largest craters on the moon. I'm going to, close in on it. I like this one because you've got, well, this is this is 144 miles across. You could fit Maine and Vermont in there. They tell me, stick them together. And I know some New Englanders that would like to, but here we have a large crater, Rutherford, on the rim, and then it just gets a little bit smaller and a little bit smaller and a little bit smaller all the way through. And it's kind of like a semicircle all the way through here. It's just kind of neat. Sometimes I look at things just for the aesthetics of it. All right, Copernicus is about 60 miles across. It's got a nice mountain range in the middle. The crater Thoth looks like a keyhole. And I don't know if you remember the first orbiter, the lunar orbiter, they called this the photograph of the century. And there is the same thing seen from an oblique angle. There's the mountain range. You could see how the edge of the crater drops down, okay? There's Thoth. If I back this up here, you can see there's Thoth and there's Copernicus in the same situation. We got a picture of this from this was taken by Ariana Matthews at the observatory using an iPhone to the eyepiece. Okay, and so one of the things we like to look at is Copernicus and Thoth is here in the same angle. One of the things we like to look at are the lunar domes that are nearby, and these are the lunar domes near Hortensius right here. You see the little hills? Okay, those are lunar volcanoes. Okay, the lava on the moon is not viscous like Earth lava. It's more like the consistency of maple syrup. Okay, so it flows out of a vast areas. When it finally does create a volcano, it's only 200 meters high, but most of them have little pits on top. We didn't quite have the ability to show the pits, but there's a whole bunch of them there, and there's a bunch near Mauritius right here. And I'm going to show you another picture right here showing. Now this is upside down. We can't always. These shows the peaks near Hortensius, and you can see the little pits. There's Mauritius, and there's a nice big one with a pit. And some of these here I've never seen. Dome land, they call it. Next time it gets around that way, I'm going to get my scope out again, see if I can pick out more of these. Okay, another favorite at the observatory is the straight wall. So here's the straight wall. I'm going to show this in detail. There's some other things you'll want to see here. The crater, well, this is Ptolemais, come on, stop doing it. Ptolemais has little ghost craters on the floor. Alphonsus was the crater that they crash landed the Ranger 7 into live on television. If you remember that, they showed it approaching and they crashed it right into it, except at the last few seconds, you didn't really see much, but they got some good close-up pictures for their purpose, even though they weren't that great. There's a lot of stuff here that's dark areas where they think were volcanic. All right, and let's see. I'm having trouble seeing at this angle here. But there's our wall. I'm going to do a close-up of the straight wall right here. You can see that there is, it's the remains of an old half-buried crater. Okay, the straight wall is just a scarp. It's 70 miles long, and it's probably several hundred feet, but it's not a sharp angle. It's more like this, okay? And here's the crater Burt, and on this side, Burt is a little rill called Rima Burt. So you've got a rill, you've got a crater, and you've got a scarp all in one picture, and you think, no, that's got to be pretty unique. You'd never see that again. But you'd be wrong, because if you go to the near the Amari Crisium, there's the same thing. The crater Cauchy, you've got the Cauchy rill and the Cauchy scarp. They call this the hyperbola. Okay, because they both kind of curve away, and that's our focal point, and these are the two curves. It's a bit of and there's a whole area of lunar domes. These two are very easy to see, and the pits are very easy to see, but the lighting has to be just right. You got to make sure you catch it at the right time and the right night to appreciate these. Okay, we're almost near the end here. Here is two craters. The brightest crater and one of the freshest craters on the moon is Aristarchus. Okay, it is at the very corner of what we call the Aristarchus Plateau. The Aristarchus Plateau is a massive volcanic area. The crater Herodotus here looks more to me like a collapsed lava cone than an impact crater. Okay, right next to it is Schroeder's Valley, which is a massive snake-like rill, which is actually a huge collapsed lava tube. I'll show you at a different angle. Okay, inside is another smaller collapsed tube. You can see the spray from Aristarchus going right over to Herodotus. I do not see debris from Herodotus. Makes me wonder what its true nature is. But it is the brightest spot on the moon. And long after it's in shadow, when they do infrared, they still can image the heat from it. So it's a neat spot. Okay, let's finish up here. Since I showed you the North Pole, again, I spend a lot of time doing, looking at libration zones because they're fun. When you get tired of everything else, you can always go to the libration. There's Clavius. Here we have one that looks like a lot like Tycho. It's a great little crater that doesn't get seen often. It's called Mortus, great little central peak. Short is here. Next to it to the left is a crater called Simpelius, which is easy to identify. It's got three little craters and a curve, and it looks like an arrow, right? You see the arrow pointing this way toward Cuvier. This one is called Schomburger. And then it takes us right up to the two southern explorers, Scott, and where's this other one? I lost my arrow, and Amundsen. So the actual South Pole was somewhere here. I use the term crater hopping when I talk about, especially near the limbs, because it's not so easy to tell the exact shape of a crater when it's so well foreshortened. So I worked my way there. So I go from Simpelius and follow the arrow backwards to Schomburger. And this is not as good as libration, okay? And there's Amundsen. This one was taken by a little orbiter, and it shows the same thing. We can go back here. We can find Simpelius. I'm gonna have to do it this way. I can't see. All right. Where is it? I've lost my little arrow. Whoops, let's back this up. Anyways, Simpelius and then Schomburger, where are we? We're off this way, because I can't see it very well. And there's Schomburger, and there is, come on, I've lost it. I can't see it. My head is twisted. Anyways, if you switch back, toggle back and forth, you can line these up crater for crater, and that's what I was trying to do. But I can't really see it the way I'm angled here. This one is Amundsen, and this one is Scott. Okay, and that's Schomburg. You can tell because it's got the four craters on the corners. All right, enough of that. Anyways, I was going to talk a little bit about the Lunar 100, and so I just took a picture of it. A lot of help that's going to do you. But if you want a good observing guide, I brought some. First of all, this little moon map. I bought a 3-inch reflector from Orion 2 years ago. Actually, I saw all but one of the Lunar 100 for EVAC with that little 3-inch Newtonian, which is it's the spherical mirror, so you can only, it's very limited in power. I used it all at 47x. I saw all but one, so I saw 99 of the objects. For the craterlets that are near, and I didn't talk about those, but the craterlets near Copernicus, when Copernicus was formed, it splattered out a lot of material and it left a line of craterlets, which are secondary craters, just big pieces of rock that flew out of the middle and landed and formed a little line between Copernicus and Eratosthenes. They're too small to see in that little scope, but I'm going to turn this in now. I figured finally I ought to get that badge. If I'm going to get toxic, unplugged it. If I'm going to give talks, I should at least have the,
Let's pick these over here,
Yeah.
so you don't have to do this.
yes. Anyways,
So we're back. So we're not back.
are we back on? Or did we lose it?
We lost something. I don't know what. Go ahead, go ahead.
Okay, and this goes starting out from day one to day, day 2, day 5, or whatever, 5-day old moon. So it's kind of a nice, it just follows through right through to the, the 28th day. And a lot of the stuff, if you miss it, when the moon is crescent, you can pick it up again after the moon is full because the shadow comes that way again. So you can see the same features again. This is probably the most definitive. That one's not definitive. This has everything you could imagine, every feature you could look for, but the pictures, they cover such a small area. Sometimes you gotta really, it's a pain in the neck trying to find the page that you want to be on. But if you need a crater and you got to know its name, this will tell you. In between is one of my most useful ones, the Hatfield Lunar Atlas, which divides the moon in sections. He draws a picture, gives the names, and then he has pictures, various pictures from different lighting conditions showing the same area. So you have to keep going back to look at the name, but it's a very useful little book. So like I say, I decided I better get my credentials back. When I did the talk at Chandler, this is back in the late 90s, I did the same talk, similar talk at one of the Chandler Parks. And when I finished, one of the women approached me. She said, "So who are you and what are your qualifications?" And I said, "I'm nobody and I have no qualifications." Which is true. I mean, it's not like, oh, I was an astronaut and I visited the moon 8 times. But no, I'm just a guy with a telescope and no cable. So what else can you do? All right, so anybody have any questions about lunar observing? Or all you all? Yeah.
You had one image there of the.
I have to get close because I don't hear it well.
You had one image there of the moon before it was deep, showing what the surface looked like.
Yeah.
Before the bar.
Yeah.
Where did they come?
Well, some guy drew it. What they did is they just studied all the masons they knew and then did their artist impression. It took a lot of research, a lot of work. And I think it's not the same. But there's several like that. But it's a pretty accurate depiction. If you spend a lot of time, this is a case where it's the exact opposite from the 1800s, but they wanted to use as much power. But where a person with just a small telescope and everybody else missing large impact basins. Oh, thank you. Okay. Yeah.
I just wanted to mention, for anybody who does have an interest in the moon, we have a globe at the observatory.
Oh, yeah.
It has everything labeled, including all the landing sites of all.
And the globes are great because, as I said, when you get near the edge of the moon, foreshortening makes it very difficult to identify craters. So you can take your globe and you kind of turn it toward you, and then you kind of turn it away and you say, okay, now I see what it is. And I've used that before. Yeah.
What size telescope do you use and what size eyepieces do you normally have?
Those are good questions. My best telescope, my favorite telescope right now is I've got an 8-inch Meade Newtonian. Okay, and I just got it. I collimated it. I gave it to her. I lent it to a friend, and he had it several years, and then he couldn't use it, so he gave it back to me. Then I got it collimated, and actually, it beats the pants off my C8. It's got great optics. Otherwise, I was using a C8, or actually, my 3-inch refractor gives me good views.
What size eyepiece?
Okay, well, all depends on the focal length. For my the 8-inch Newtonian, I use a Teleview 3 to 6 power zoom. And when it gets down to 3 millimeters now, I'm at, let's see, 400x. And that's about the limit I sometimes use a 12-inch Newtonian, and if I boost it up to 600x, I can see things like Ina Caldera, the D shape, or I can see the little rill and the Alpine Valley. But the seeing has to be superb, and you don't get that kind of seeing in Arizona very often. So sometimes it's not worth hauling out the big 12-inch when it's not going to do you any good. Anything? I thought I saw somebody's hand go up. Okay, well, thank you.
So thank you, Don. Our next meeting is September 16th. Our speaker is Kevin Schindler. So we look forward to seeing you there. If you can assist us in taking up chairs, that would be wonderful. Have a lovely evening. Thank you, Don and Steve, for some really great presentations. Thank you and good night.